three different ways of defining probability. The first one would be classical definition of probability. Second one would be frequency interpretation of probability. And the third one is axiomatic definition. Axiomatic definition. Okay, we shall look, or we shall go into each way of defining the probability one by one. The first one would be classical definition. Now, the probability P of A of an event A is determined by NA by N, where NA is total number of favorable outcomes and N would be total outcomes. Now, the probability of an event equals the ratio of its favorable outcomes to the total number of outcomes, provided that all outcomes are equally likely. The key word in this definition is equally likely. Please remember this one. Okay, I repeat the definition again. The probability of an event equals the ratio of its favorable outcomes to the total number of outcomes, provided that all outcomes are equally likely. Now, this seems a pretty good definition, but still it has got its own critics. The critic would be, these are the follows. Now, the first one word would be the usage of the term equally likely. Equally likely means equiprobable. Now, we are trying to define what probability is, but still when defining that term itself, we are using the word equiprobable, which doesn't make any sense because the definition is using the concept to be defined. We are trying to define what probability is, but in the definition we are using the concept itself, because the definition says that all the outcomes should be equally likely, which means all the outcomes should be equiprobable. When we are trying to define probability, we are using the term equiprobable, which doesn't make any sense. And the second one would be, if the total number of outcomes are infinite, then how to define it? If the outcomes are infinite, how to define it? Okay. And the third part is, or the third one is, we can calculate the probability even before conducting the experiment. Suppose I say, what is the probability of a 3 coming up when a die is rolled? I can calculate the probability of its occurrence without even conducting the experiment, because the favorable outcomes would be 3 out of 6. Out of 6 outcomes, 3 occurs only once. So I can say that the probability is 1 by 6. I can say that without conducting the experiment itself. So I can define the probability even before conducting the experiment. Okay. Now the fourth one is n, the terms or the numbers n and a are not always clear. Okay, n and na are not always clear. For example, look at this problem. Find the probability P that sum of two numbers when two dice are rolled is 7. When two dice are rolled is 7. Okay. Now let's see how n is defined. I would define n to be the sum when two dice are rolled. The sum can take 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. It stops here because the least number of two on two dice would be 1 plus 1, it would be 2. So sum cannot be 1 and the maximum sum would be 6 plus 6, 12. Now if I say n is 12, if I define n in such a way, now my NA would be how much? Only 7. So total number of favorable outcomes would be 1, 2, 3, 4, 5, 6. Sorry, it's not favorable. Total number of outcomes would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Whereas favorable outcomes would be 1. So P would be 1 by 11. But it doesn't make sense. We'll see why. Because this, the favorable, the total set or the sample space, or let's say the total outcomes should be exhaustive. Here sum of 7 can occur more than once, or let's say more than one way. If it shows a die 3 on one die and 4 on another dice, the sum would be 7. And if I flip the dice or the numbers on the dice, if it shows 4 on the first die and 3 on the second die, the sum is again 7. If it is 6 on the first die and 1 on the second die, the sum is again 7. So n is not exhaustive. That means it has not accommodated all the possible outcomes. That is one way. Okay. Now another way of interpreting n is consider the pairs without repetition. Okay. Pairs without repetition. So there would be 21 pairs, of which 3 are favorable. So probability that I define is 3 by 20, that I come up with is 3 by 21. If you observe, the answer is quite different from what you got in part A, because by defining the value of n in two different ways, I am getting two different probabilities. But still, these two n's, the two different ways in which I had defined n, are not correct, because without repetition doesn't make any sense. Without repetition in sense, remove 1, 1, 3, 4, 4, 3. Okay, they are repeating it, but still that doesn't make any sense. Now it would give us a correct probability if we determine, if we consider each outcome as equally likely. That is, if we consider n as equal likely, that means each outcome should be equally likely. That means the probability of occurrence of 4 on one die and the probability of occurrence on 3 on one die is same. Likewise, the probability of occurrence of 3 on one die and 2, 4 on the second die is also the same. Okay. Now there would be total number of 36 pairs, and NA would be 6 pairs. Therefore P would be 6 by 36, that is equal to 1 by 6. See, in this case we have three different ways of interpreting n and NA. So that's the problem with classical probability. Okay. Now the next definition is frequency interpretation. Now the probability of occurrence of an event PA is limit n tends to infinity NA by n. It's almost the same, but it requires that the experiment to be performed repetitively over and over again. That means if I perform an experiment once, I'll determine NA and N. If I repeat it again, I'll get another NA and N. So likewise, if you repeat the experiment over infinite times, it will come up to a value that is called as the probability of the event A. Now where is it used? It is used, for example, it is used for computing the average symbol error probability in digital communications. In this particular definition, okay, in this particular definition, the probability is estimated. Okay, understood? In this, when we are trying to define probability using this concept, the probability here that is obtained here is estimate probability. Now, frequency interpretation of probability allows to estimate probability when classical probability provides no insight. Frequency interpretation of probability allows to estimate probability when classical probability provides no insight. Okay. Now, the third and the most important way of defining probability is axiomatic definition. Axiomatic definition. So what does axiom stand for? Basic properties of math variables are called as axioms, and theory is developed from axioms. Basic properties of math variables are called as axioms, and theory is developed from the axioms. Okay. Now, axiomatic approach build up probability theory from a number of assumptions. Okay. See, we come up with certain assumptions and they hold true, and we expect them to hold. We expect them to be true. So, basing on those assumptions, we will build up theory. Now, its theory is based on three postulates. What are those postulates? The first one would be the probability of occurrence of an event A greater than 0, and P of A lies between 0 and 1. Okay. Now the probability of a sample space or total set is 1. Now the third postulate is if the events are mutually exclusive, then P of A union B equal to P of A plus P of B. These are the three postulates or axioms, and using three axioms we'll define the probabilities theory, or we'll define what probability is. But in order to define probability using three axioms, we should be knowing the basics of or the fundamentals of set theory. Okay.